This is a race for global technological supremacy. The United States is striving to establish a complete rare earths industrial chain, spanning mining, smelting, and separation, through to magnet material manufacturing. Simultaneously, China is tackling the ultimate challenge in semiconductor production: extreme ultraviolet lithography. These two seemingly unrelated technological objectives both converge on a single core issue: how to break the other's strategic monopoly in critical technological domains. The dilemma of pursuers on parallel tracks. The complexity of the rare earth supply chain is often underestimated. Extracting rare earth elements from ore is not inherently difficult. The true technological barrier lies in the smelting and separation stage. Isolating each of the 17 chemically similar rare earth elements requires hundreds of extraction cycles. Through decades of technological accumulation, China now controls over 90% of global rare earth refining and separation capacity, achieving unit costs merely one-third of overseas competitors. Lynas Corporation of Australia incurs mineral extraction costs 2.8 times higher per kilogram than Chinese enterprises, and this represents merely the starting point of the industrial chain. America's Rare Earths Revival Plan commenced in early 2020. California's Mountain Pass mine, operated by MP Materials, stands as the nation's sole active rare earths facility. The company reactivated its integrated processing plant in 2023, commencing production of high-purity neodymium-praseodymium oxides. In July 2025, the U.S. Department of Defense announced it had become MP Materials' largest shareholder, investing $35 million to construct a heavy rare earth separation workshop on site. This marks America's first attempt to restore refining capabilities for critical heavy rare earth elements like dysprosium and terbium. Yet even under the most optimistic projections, industry consensus holds that mastering the entire industrial chain, from initial separation to full technological autonomy, will require at least 15 years. This timeframe is not arbitrarily estimated. Rare earth separation processes involve complex chemical flow control, environmental treatment, and product purity management, each requiring extensive experimental data and accumulated engineering expertise. China's journey from initiating rare earth extraction and separation research in the 1970s to establishing global dominance by the 2010s spanned over 40 years of sustained investment. More critically, rare earth smelting generates substantial wastewater containing radioactive waste, with environmental compliance costs potentially accounting for 30 to 40% of total expenses in Western nations. MP Materials' Texas facility currently produces only neodymium-praseodymium metals and prototypes magnets, leaving multiple critical links unresolved in establishing a complete closed-loop process from mining to magnetic material manufacturing. By contrast, the technical complexity of EUV lithography machines operates on an entirely different scale. These devices require a 20-kilowatt laser to continuously bombard molten tin droplets, just 20 micrometers in diameter and falling at 50 meters per second, to generate 13.5 nanometer extreme ultraviolet light. The entire optical system operates in a vacuum environment, where the flatness error of the core reflective surface must not exceed 0.1 nanometers, equivalent to controlling the undulations of Earth's surface to the size of a golf ball. Dutch firm ASML commenced EUV research and development in the 1990s, launching its first prototype only in 2010 and achieving commercial mass production in 2019. This journey spanned nearly 3 decades, with R&D investment exceeding €6 billion. China's publicly disclosed EUV advancements reveal a distinct technological approach. According to 2025 reports, the Shanghai Microelectronics-led project employs laser-induced discharge plasma technology, differing from ASML's laser-generated plasma solution. This approach claims to reduce equipment size to one-third of ASML's models, with light source stability fluctuating by merely 0.8% over 100 continuous hours. According to the schedule, the first prototype SMEE 3600 is slated to commence stress testing at Huawei's Dongguan facility in the third quarter of 2025, with mass production targeted for 2026. However, these reported technical details remain unverified by independent sources. Moreover, transitioning from trial production to stable mass production typically requires several years to resolve engineering challenges such as yield rates, reliability, and supply chain integration. The contest between industrial foundations and time dimensions. The fundamental difference between these two technological challenges lies in their nature. The rare earth supply chain involves experience-intensive and capital-intensive traditional chemical processes, whereas EUV lithography machines represent knowledge-intensive, precision-manufactured integrated cutting-edge equipment. This distinction determines their fundamentally different bottlenecks. The greatest obstacle to rebuilding America's rare earth supply chain is not isolated technological breakthroughs, but the absence of an entire industrial ecosystem. China's rare earth sector is underpinned by a comprehensive system comprising 6 state-owned conglomerates, hundreds of downstream enterprises, and tens of thousands of skilled technical workers. Take ion-type rare earth mines in Guangzhou, Jiangxi as an example. From in-situ leaching and mother liquor collection to impurity removal, each stage involves specialized equipment suppliers and technical service providers. Such industrial support capabilities cannot be replicated elsewhere in the short term. Although Lynas Corporation owns mines in Australia, its separation plants still rely on facilities in Malaysia and the United States, with production ramp-up progress consistently lagging behind expectations. The disparity in time costs is even more pronounced. Even if MP Materials' heavy rare earth separation plant is completed without hitches, it can only process output from the company's own mines. Yet a single F-35 fighter jet requires 400 kilograms of rare earths, an Arleigh Burke-class destroyer consumes 2.36 tons, and an aircraft carrier demands 4 tons. With U.S. rare earth consumption projected at 40,000 to 50,000 tons in 2024, reliance on a single mine falls far short of meeting demand. Expanding production capacity necessitates developing additional mines and constructing more separation facilities. Each new project requires at least 5 to 7 years from environmental impact assessment approval to operational commencement. Given that China's Ministry of Commerce has included the entire rare earth industry chain, encompassing equipment, technology, and raw/auxiliary materials, within its export control scope since 2025, American enterprises can no longer accelerate construction by importing Chinese equipment. Independent technological R&D will further prolong the timeline. The challenges surrounding EUV lithography machines center on breakthroughs in a handful of core technologies. The light source system, optical lenses, and workpiece stage constitute the 3 core subsystems, each demanding cutting-edge capabilities in physics, materials science, and precision engineering. ASML's success rests upon a global supply chain collaboration. Optical lenses supplied by Germany's Carl Zeiss, light source systems by the US-based Cymer, and photoresists and masks by Japanese firms. This global division of labor implies that any single nation seeking to independently develop EUV technology must simultaneously overcome multiple world-class technical hurdles. China's accumulated expertise in lithography equipment remains relatively limited. Semicon Shanghai currently mass-produces ARF dry lithography machines for 90-nanometer processes, while its 28-nanometer immersion equipment remains in the R&D phase. The transition from 28-nanometer DUV to 13.5-nanometer EUV represents not merely a change in wavelength, but a generational leap in the entire technological ecosystem. Even if Semicon's claimed technical pathway proves viable, transitioning from laboratory prototypes to industrial production equipment requires resolving thousands of engineering details. ASML's NXE 3400 series lithography machines comprise over 100,000 components. Instability in any single element could render the entire system incapable of achieving the yield rates demanded for mass production. The more pressing reality is the urgency of the time window. Semiconductor process advancement follows the inertia of Moore's law, with TSMC already planning 2 nanometers and 1.4 nanometers nodes based on its 3 nanometers process, all reliant on the latest generation of EUV equipment. Should China fail to achieve substantive breakthroughs in EUV technology by 2030, the generational gap with global advanced processes will widen further. For America's rare earth industry, the early 2030s marks the critical phase when key facilities commence operations. Yet whether China's rare earth production advantage has by then solidified into a permanent cost and technological moat will directly determine the commercial sustainability of American rare earth enterprises. Asymmetric advantages in strategic rivalry. In terms of absolute technical difficulty, manufacturing EUV lithography machines is clearly more challenging than establishing a rare earth supply chain. The former represents one of humanity's pinnacle engineering achievements, while the latter involves mature industrial processes. Yet the introduction of the time dimension alters this assessment. China's advantage in rare earths has solidified into a supply chain moat. Even if the U.S. establishes a complete domestic supply chain by 2030, its product costs will remain significantly higher than China's. This cost disparity stems not only from labor and environmental expenditures but crucially from economies of scale. China's annual production capacity of 240,000 tons of rare earth oxides dilutes fixed costs, enabling efficient operations across every stage. More significantly, China controls downstream magnet material manufacturing, accounting for 90% of global neodymium iron boron magnet output. Even if the U.S. succeeds in separating rare earth elements, its strategic objectives remain unattainable if magnet processing continues to rely on imports. Yet the risk of rare earth substitution cannot be overlooked. While electric vehicle motors and wind turbines currently rely heavily on rare earth permanent magnets, Japanese and European firms are developing ferrite magnet and rare earth-free motor technologies. Tesla announced in 2023 that certain models now employ rare earth-free permanent magnet synchronous motors. Should such alternative technologies achieve breakthroughs within the next 5 to 10 years, the growth trajectory of rare earth demand could decelerate, thereby diminishing China's strategic leverage. In contrast, semiconductor manufacturing processes remain dependent on extreme ultraviolet (EUV) lithography with no foreseeable alternatives, rendering EUV lithography machines a more rigid strategic bottleneck. China faces more pressing time constraints in the EUV domain. The semiconductor industry's rapid iteration means technological windows remain open only briefly. Failure to establish stable mass production capabilities by 2030 risks being left behind as the global semiconductor sector advances into the 1-nanometer or sub-nanometer era, where catching up becomes exponentially more difficult. Moreover, technological restrictions on EUV lithography systems are intensifying comprehensively. In 2024, ASML extended export controls to certain DUV equipment destined for China. The Trilateral Export Control Coordination Mechanism established by the United States, Japan, and the Netherlands has effectively blocked China's path to reverse engineering through equipment imports. In contrast, the U.S.'s rare earth supply chain development, though progressing slowly, follows a clear trajectory. Direct investment from the Department of Defense, policy support under the Defense Production Act, and resource partnerships with allies like Australia and Canada provide multiple safeguards for its industrial reconstruction. Even if China imposes export controls, the U.S. could sustain its supply chain by absorbing increased costs. More significantly, rare earth strategic value lies primarily in military equipment and high-end manufacturing, sectors relatively insensitive to cost pressures. The Department of Defense's willingness to pay premiums for domestic rare earths provides stable demand support for industrial development. The verdict of time. If the question is simplified to who will be faster, the answer hinges on how completion is defined. The United States may establish a functionally viable rare earth supply chain by 2030 to 2035. China may produce an EUV prototype operational in laboratory settings by 2028 to 2030. However, if the benchmark is establishing internationally competitive commercial production capacity, both nations face extended timelines. Even upon full completion by 2035, the U.S. rare earth supply chain's product costs could remain 1.5 to 2 times higher than China's. This cost disadvantage would constrain its market share during peacetime. Only when geopolitical tensions escalate and supply chain security becomes paramount would the strategic value of a domestic supply chain fully manifest. Even if China achieves a technological breakthrough in EUV lithography by 2030, resolving issues such as yield rates, equipment reliability, and component localization would require a further 5 to 10 years from the first unit's production to establishing stable industrial-scale supply. ASML similarly underwent nearly a decade of engineering refinement from its first EUV prototype in 2010 to mass commercialization in 2019. A deeper concern lies in the fact that this race lacks a fixed finish line. Technical barriers in the rare earth sector are steadily lowering. As extraction techniques become more accessible and environmental standards evolve, more nations may acquire smelting and separation capabilities, gradually eroding China's monopolistic advantage. Meanwhile, semiconductor process evolution continuously raises the bar, from EUV to high numerical aperture EUV, and potentially next-generation technologies like extreme ultraviolet interferometric lithography. Each generation sees exponential complexity growth. This means China's pursuit in lithography equipment is effectively a race against an accelerating target. From a strategic perspective, these two technological objectives serve distinct purposes. America's reconstruction of its rare earth supply chain constitutes a defensive strategy, aimed at avoiding strategic choke points in future conflicts. China's pursuit of EUV mastery, conversely, represents an offensive objective, an attempt to shatter the adversary's technological monopoly at the apex of the semiconductor supply chain. Defensive strategies can tolerate higher costs and extended timelines, as their core value lies in strategic insurance rather than economic efficiency. Offensive objectives, however, demand breakthroughs within a specific time window, otherwise technological generation gaps will render the pursuit futile. Ultimately, this contest may yield no definitive winner. America's rare earth supply chain will establish its fundamental framework by the mid-2030s, yet it will never compete cost-effectively with China. China's EUV technology may achieve breakthroughs around the same period, though catching up to ASML's comprehensive technological prowess will require further time. Neither objective will fundamentally reshape the global technological landscape. Instead, they will propel Sino-American technological competition into a new, more complex equilibrium. Within this new equilibrium, technological autonomy ceases to be absolute and becomes relative. Time is no longer a straightforward disadvantage for the follower, but rather a test of strategic patience.